Hello and welcome to this guide. This will be the third video in a series showing you how to make and use a simple acoustic measurement setup in the workshop. In this video we will go over downloading, installing and setting up the ObieApp, the general measurement principle involved with all measurements you can do with this setup, connecting and configuring the measurement setup on Windows-based systems. We will then go through step by step and perform an inner cavity measurement, a radiation measurement, an admittance measurement, and a general transfer function using a violin top plate as an example. In another video we will talk about how to interpret the results of your measurements. For now, let's focus on how to get them. As you can see, there's much to be done, so let's dive right in. I have included the link to the ObieApp's Google page in the description of this video. It will take you to the home page. Here you can find many useful resources regarding the ObieApp. For now we are interested in downloading, so let's click on 2.2 Software Setup. In the blue banner there are download links for macOS, Windows and LabVIEW users. Choose the appropriate one for your system. Here I can only show the installation process for Windows users. The link will take you to a Google Drive folder where you can download the latest version of the ObieApp. At the time of recording this is B38. I will download the zip file and then locate it in my downloads folder. Newer versions of Windows can unpack such files by default. Simply select the file, right-click and select Extract All. Alternatively, you can click Extract All in the upper selection bar. This will prompt you to specify a location to where the contents of the zip file should be extracted. I will opt to extract to the current folder, which is my downloads folder. After a short time, you will see the extracted folder containing the ObieApp installation files. Simply double-click the install.exe, allow the prompt, and install the software with standard settings. At this time you may be prompted to restart your machine, so do this before continuing on. After installation, you should be able to open the ObieApp either through the shortcut on your desktop or by pressing the Windows key and beginning to type ObieApp. Once you have the software running, you will be greeted with this screen asking you to define the measurements folder. This will be where the ObieApp stores all the data you will collect with it. Here I choose a folder on my desktop. Back in the app, there are many buttons to click and functions to explore, so it may seem somewhat overwhelming in the beginning. Let's go through the most important things you need to know. In the upper left-hand corner you have the primary function buttons. These are designed as drop-down menus and will allow you to begin measurements, open a testing environment called Scratchpad, and configure the software preferences. Below this is a currently empty space that will list all of your measurements once there are any. The big graph on the right hand side will display these and allow you to compare among them. For this tutorial, these are all the areas of the software we need. As you can see, clicking on New Test reveals a list of names. From the names, you might be able to guess that these are meant for different types of measurements. What we are selecting here is called a template, and what it is a simple list of all the settings necessary for a specific measurement. On the project's GitHub page you can download one of these templates that I have made for use with the general measurement setup. You will then need to move it to the settings folder within the ObieApp's data folder. You can see the other templates that showed up in the ObieApp are already there. Now if you go back into the software and click on New Test, you won't see any change. The app first needs to update its list, and for that it needs to restart. So let's close it for now, and before we open it back up, let's connect the Soundcard. Don't worry about connecting the measurement setup to the Soundcard for now. I just wanted to show up in the software so we can see it in the next step. Once back in the ObieApp, the GMS template shows up in the list of templates as it should. Additionally, if we go to Settings, Preferences, we should be able to select the Behringer interface as a device. It will show up as USB audio codec. Click OK to accept the changes and close the window. Now go to New Test and select the GMS template. Of course, we will not be able to do an actual measurement right now. I just want to show you what the procedure will be like. A window labeled New Test will pop up that allows you to label the measurement. The first field asks for an instrument name. For the purposes of this demonstration, I will enter Testing for video. The test name field will automatically be populated with this name and a number behind it. As I have done 6 of these tests already, it will add a 07 to the end. Of course, you can change the test name if you want to. Under Instrument Notes, by default I have left this section empty in the template. You can add information such as the date and time, the place, or maybe how you thought the instrument sounded at that stage. It's up to you. Here I will simply write, "This is a test for the video demonstration." Once again, here you can make sure that the correct recording device is selected. Below that, all the settings in the template are shown. Let's not get into that now though. Click OK in the lower right hand corner to get to the measurement view. This is the window in which all the actual measurements will take place. You might have seen it before in the first 2 videos of this series. In the upper left hand corner, 2 blue bars show the current level of the 2 Soundcard channels. Currently we don't see anything, of course, as there is nothing connected to the interface. The 2 lower fields will show the time signal of both of the channels. I have overlaid what they should usually look like for our measurements. The hammer signal is a very short and sharp tap, while the microphone signal decays more slowly, forming a slope. Both will be transformed to a frequency domain, and the ratio between them will be displayed in the right-hand graph. Now, this brings me to the general principle involved with all measurements we will discuss today. Why do we measure 2 different signals and then display the ratio between them as our result? Well, the problem that we are solving by this is simple. We need to excite the instrument in some way so we get a signal out. For this to be representative, we would either need to know the input signal or be sure that it is exactly the same every time. While we could try to make a pendulum fixture that puts each instrument in exactly the same position every time and try to prevent its mass and friction properties from ever changing, this is just much more difficult than recording the input signal. In this way, the excitation doesn't have to be exactly the same every time. A slightly weaker excitation will result in a weaker output signal, and a slightly stronger excitation in a stronger output signal. The ratio between them stays the same, so the result we are presenting is independent of the excitation signal's strength. Within some limits, of course, which we will discuss more in the future. But for now, rest assured that excitations such as those that we can achieve with the measurement setup, while not being identical at all, are well within the limits for this principle to apply and provide useful results. Another requirement for doing informative measurements is that the instrument needs to be excited evenly at all frequencies of interest. We are not interested just in what the instrument is doing at, say, 400 Hz, but over a wide frequency range. So we cannot just excite it at one frequency at a time, but rather all of them simultaneously. An impulse like the one we are generating with the hammer can fulfill this requirement to an extent. Here's the time signal of the hammer. We can see that it is a very short burst of energy. In theory, were it infinitely short, its energy would be evenly distributed over all frequencies. So the frequency transform of the time signal would look like this, a flat line. Of course, and as you can see for yourself, in reality, the impulse is not infinitely short. We can guess that this is about 1 millisecond long. Therefore, the actual frequency transform of this time signal looks much more like we see here, rather than a flat line that would be ideal. Now, relatively speaking, this is still somewhat flat, but towards higher frequencies we can see that we get less and less energy. The ObieApp provides a rule of thumb for estimating how little energy is too little, by way of this gray area. We can see that our excitation signal drops into this area at about 7 kHz, so our measurements are good at least up to that frequency. Still plenty useful, but we should be careful and keep an eye out for this plot. It can often explain why you might have trouble with a given measurement. We will average multiple of these measurements to get more accurate results. As soon as you excite an instrument the second time in a given measurement, another function will show up next to the actual measurement result. This is called the coherence function, and what it is basically a mathematical comparison between the individual signals we are creating with each excitation. If they are identical, the value of the coherence function will be 1. If they are very different, the value of the coherence function will be closer to 0. So what this line on the graph tells us is if the individual measurements we are using to create an average are actually quite similar to each other, which they should ideally be. This can help us to determine if a given measurement is useful, such as this one, or not very useful, such as this one. There's a convention for setting up the hammer to excite a violin at the bridge. Now technically, measurements that use a different convention are not incorrect, but they are hard to compare. The convention I will show here is established and has been chosen for good reasons, so I suggest you follow it too. I will bring the hammer in line with the upper bass side corner of the bridge. Then I will drop it slightly so that the contact point between the hammer and the bridge is about 1 mm below the upper end of the bridge. The hammer should hang vertically when in contact with the bridge. Test out the excitation beforehand. Oftentimes you will be able to hear if it makes solid, short impacts. Here are some examples for you to listen to. And here you can see the hammer hitting the bridge in slow motion. You may be able to tell that the contact time is not 0. To get closer to this theoretical ideal, we could either increase the hardness of the hammer tip or that of the object we are hitting. The excitation signal of a steel-tipped hammer on a steel object actually turns out to be completely flat up to very high frequencies. Okay, almost done with preparations. Before we can begin with some actual measurements, we need to set up the sound card correctly. Hit the Windows key and begin typing Change System Sounds. You should see this as a suggestion, even if your system language is not English. Once we click on this suggestion, the sound settings window will open up. It contains 4 subcategories. The one we are interested in right now is of course called Recording, so click on that. Most likely, multiple devices will show up here. Look for the one that is called USB Audio Codec. Select it and click Properties in the lower right hand corner. Here let's first go to the Advanced tab and make sure that the default format is set to 2-channel 16-bit 48,000 Hz DVD quality. Oftentimes Windows will default to single-channel operation with recording devices like this. Now go to Levels and adjust the slider to 50%. With that done, we can close this window and apply our settings by clicking OK twice. Finally, we can get to our first method, the cavity measurement. Plug the microphone arm and pendulum hammer into the input channels of the USB interface. The ObieApp template is configured so that the left channel, white change connector, is the microphone and the right channel, red change connector, is the hammer. I support the instrument at the lower end using 2 pieces of foam. These are from a cut-up kitchen sponge. They should be bouncy and not too dense. I will use another piece to support the violin at the neck. Test that the instrument is freely supported by tapping on the neck and observing its vibration. For the measurements discussed today, we will dampen the strings. Here I have prepared a piece of paper to wedge between the strings. You can also use light foam blocks. Now bring the hammer into position as shown earlier. Then insert the microphone through the bass side F-hole. For this you will have to remove it from the microphone holder and carefully thread it through. Here's a cross-section through the instrument that shows you how it should sit. The microphone itself should end up roughly centered in the instrument, and the straight section of the S-shaped microphone arm should pass through the F-hole without touching the edges. You have 2 ways of adjusting this position. The microphone holder can slide up and down the aluminium rails, and the microphone arm can slide forwards and backwards in the microphone holder. Once you are satisfied with both the microphone and hammer positions, in the ObieApp, go to New Test and select the GMS template. Name and describe your test and hit OK to get to the measurement screen. Pull back the hammer with 1 finger and let it fall against the bridge of the violin. After it has made contact, catch it again to prevent it from hitting twice. Repeat the excitation 5 times and the ObieApp should let you know that your measurement is finished. Now hit OK and save, and your measurement result will be saved to your hard drive and displayed in the ObieApp. The second method will work in much the same way. The only thing we will change is the position of the microphone. Again, plug in the equipment if you haven't already. Support the instrument at both the lower and upper ends using soft foam. Dampen the strings in your preferred way. For the radiation measurement, we will move the microphone holder above the slider component and rotate it by 180 degrees as shown here. For this to work optimally, the slider should be installed so that the linear bearings are pointed downwards. Now clip the microphone arm to the microphone holder with the microphone pointed downwards. If you want to do repeated measurements like this and be able to compare them later, you will need to decide on a standard microphone distance. Here I adjust the distance from the top plate to 150 mm. Now, as before, we can position the hammer and take the measurement. The third method I will show today is the admittance measurement. Here we will measure the transfer function between the bass and treble side bridge corners. Plug in the equipment, support the instrument on soft foam pads, and dampen the strings. Now take the small accelerometer that we made in the last video. We will glue it to the treble side bridge corner using superglue. I will add a small drop of superglue to the microphone before bringing it anywhere near the instrument. I recommend you to do the same. Getting superglue on the varnish at this step would be unfortunate. Once the glue has set, we can position the hammer correctly and start the measurement. The last method for today is the general transfer function. I will show the example of a violin plate. This is a CNC cut top plate. Keep in mind that this is a general method, so it could be used for many other applications. For example, I use it to record the vibration properties of top and back plate blanks. From this, the material parameters can be deduced. For every transfer function measurement, you will want to support the object freely, as we did before. Here I use 4 soft sponges to support the top plate. Then I plug in the equipment and glue on the accelerometer using a small drop of superglue. The position of excitation and recording are important here. If you place either on the nodal line of a given mode, this mode will not be well represented in the measurement result. For plates like these, the edges are generally a safe guess, as you will avoid most of the nodal lines there. I place the accelerometer just inside of the gluing surface. I support the cable with a small clamp to remove some of the load from the plate. Now we are ready and the plate can be excited. I will excite it in a similar place in the upper bout. You see me use an older version of the handheld hammer here. This does not influence the measurement result meaningfully in this case. However, as we can tell from both the hammer input signal and the coherence function, this result would only be useful up to about 1 kHz. This is perfectly useful for violin plates. Okay, that's 4 useful workshop measurements for you that you can perform with the general measurement setup. Of course, the burning question is, what can you now do with the results of these measurements? There are already some useful resources out there, which I will link in the video description. But it will certainly also be the topic of future videos on this channel. For now, this series is concluded, and I hope it is helpful to you. As always, let me know what you think and what you would like to see next. Until then, Luca.